All right, let's consider the isothermal expansion of a perfect gas. And let's consider it in two ways, this process done in two ways. The first, indicated here, a two-step expansion. And we know that if the gas is expanding, and here it's doing so isothermally, if it's doing so in two steps, or one step, or 5 steps, this is an irreversible process. And so we're being asked for the work associated with this process. So right away, we know that, let me just draw a line here, just to jot down some thoughts. We know that in any case, that work is equal to a minus PdV. And we know that for the irreversible process, like that one described in this first part, I'm going to spare you all the integration here because that's done somewhere else, that this work is equal to a minus P external, which is also the final pressure of the gas, times delta V, the change in volume. And we know that for the corresponding reversible isothermal process, that this would integrate a little bit differently. And I'm just again going to put a circle around all these negative signs. They don't look like marks on the paper only. nRT ln of V final over V initial. Okay, so that's where we're going with this. Now we can get started. And although it doesn't say it here, it might ask you to sketch what these look like on a set of pressure volume axes. And in fact, that is part of this tutorial. To do that, I just have not written it in above. Okay, so let's get going then on the solution to the first part. And let's add to what's written in the question, because I believe it's the intention, is to incorporate the sketch on a pressure volume set of axes. I'm leaving a little bit of room here because I want to add some graduations and labels. Let's decide on where the starting point for an isothermal expansion would be. Think about the change in volume. What would delta V be for an expansion? Would it be greater than 0, a positive value, or would it be less than 0, a negative value? For expansion, delta V is going to have a positive value, right? So I want to leave some room for, excuse me, for the volume to increase. So my initial volume is going to be to the left of my final volume. So I'm over here in this part. Now think about the pressure. How will the pressure change in an isothermal expansion of a gas? I need to keep it the same temperature. The gas is doing work, pushing that lid on the piston up. What's going to happen to the pressure if the temperature is maintained? The pressure will drop, right? Sometimes, and thermodynamics is good for this, if the more intuitive situation is the reverse, then think about it in the reverse and then make the appropriate changes to your final answer. What I'm getting at there is if we thought about compressing the gas, it would, yeah, it's very intuitive that the pressure would go up. And so the pressure is going to drop. So I'm up here for P1 and down here for P final. So I'm just going to put a dot here as my starting point. Okay, and if I look at the given, the starting point is 2 liters and 6.25 atmospheres. So my volume is in liters and my pressure is, I'm going to list in atmospheres. So my first mark then is 6.25 and my mark for the volume is 2.00. I'm doing this in 2 steps. So let's make a mark for, if that's 2, let's put 4 liters, and then finally 6 liters roughly. Convincing, not exact scale, but anyway. And the pressure, 6 1/4. So there's about, say, 3, but I want 3.50 for the pressure. So I'm going to go just a little bit up, 3.50. And then finally 1, somewhere here. Okay, good. Let's go through the process without making any marks on the page just yet. So I'm starting here, 2 liters, 6 1/4 atmosphere. And the system is undergoing an expansion, an irreversible expansion, which means that the pressure that it is expanding against is equal to the final pressure of the gas. What is the final pressure of the gas in that first step? If you look at the given, it's going from 2 and 6 1/4 to 4 liters and 3 1/2. Right. So think about it as in the process that this, piston system is stable. It's not moving. I have mechanical equilibrium with a gas occupying 2 liters and a external and internal pressure of 6.25 atmospheres. If I change that external pressure suddenly to equal 3.50 atmospheres, then the gas system is going to respond, and the response is that it's going to expand its volume, not straight across isobarically, but have a pressure drop in the process. And so although I've made a mark here, my starting point for the expansion is, the volume has not started to expand yet, but I did have to change the pressure because there's no incentive for change here. So we drop the pressure to 3.5 atmospheres on the outside of the piston, and the gas expands. And now it's expanding against a constant, yes, pressure, all right? A constant external pressure, which is equal to that of the gas. And I'm dropping my perpendiculars down here to indicate the area, if you like, under the curve, although it's a flat line. And this area under the curve is equal to the work of the first step. That is step 1. Step 1, I have a gas that's expanding from 2.00 to 4.00 liters right across against a constant pressure. P is equal to 3.50 atmospheres. Okay, so I was here, we changed the pressure, suddenly the gas expanded, and now it's going to expand against a constant external pressure in the second step, because it's going from 4 and 3.5 atmospheres to 6 liters and 1 atmosphere. So I'm going to make that mark there. So in fact, it's doing something like this, a little the step function, and then like so. But again, I'm going to drop those perpendiculars once again, and put the lines this way. And this is my step 2. So there's step 1, there's step 2. So the work of the second step is captured in this little rectangle here. And the work is minus P external delta V. So again, that P external is 1 atmosphere, and there's my delta V. In this step, my P external is 3.50 atmospheres, and my delta V is 4 minus 2. So do you see that it's really mapping out the area of the rectangle of dimensions P external delta V? And then the work of the second step is the area of the rectangle, and therefore P delta V. And I'm going to add those two works together, if I can use that as a plural. And actually I'm going to put it underneath here. Be careful not to go off the screen, and then we'll do number 2, the corresponding reversible work, on the right hand side of the page. Okay, so if we were asked to sketch out those steps on a set of pressure volume axes, like any set of axes, we want to make sure that they are labeled, and then the points are labeled with appropriate precision, at least the ones that we know. It's not exactly to scale, but it makes sense. All right, so now my total work is going to be equal to the work of the first plus the work of the second step. So let's call it W1, the work of the first step, and we know it's equal to that minus P external delta V. My P external is 3.50 atmosphere. That's how many atmospheres it is. Delta V, so open bracket, making it very clear that this is a change, although I can do that in my head and say it's 2. I'm just going to write it out. 4.00 minus 2.00. And then I'm going to close the bracket and put the unit on the outside. Good practice. And before I jump to the next line, and I want to throw this in the calculator, or not, and calculate my work, I'm looking at the units, which I always do at this point. I want to see if I can cancel anything, and clearly there's nothing here because I'm just multiplying 2 things together that each has single units. So I'm going to have an answer of liter atmospheres, or atmospheres times liter, if you like. That doesn't sound like work. Now remember, in assessment situations, we're always given the value of the gas constant R, specifically 8.3145 joule per K mole, and 0.08206 liter atmosphere per mole K. And we'll notice that the ratio of those two gives us actual units, a conversion factor for how many joules correspond to a liter atmosphere. So I'm going to do that right away, and the ratio of the two is 101.3. The conversion factor is 101.3 joules per liter atmosphere. Okay, so I don't want to calculate and then do another calculation on my final answer. I want to do it all at once. Push this up here in better view. And so atmosphere, liter go out, and I'm left with joules. Great. Now I'm ready to put this in the calculator. And I get an answer of, I'm carrying that negative sign, 709.1. I should have 3 significant figures. I can also choose to write it 7.09 times 10 to the power of 2 joules, which clearly shows 3 significant figures. That's the work of step 1. And similarly, there's a dot on the page here, work of step 2 minus P external delta V. Okay, go ahead and calculate that. I will, right here, we'll compare our answers. P external delta V just for the second step. Conversion factor. Demonstrate unit cancellation. Demonstrate that the correct units will follow. And twice that. 202 negative 202.6 joules, which in 3 significant figures becomes 203. And it is negative. Energy is leaving the system as work when it does an expansion. 2.03 times 10 to the power of 2 joules, if you like to use scientific notation at this point. And so the total work is equal to work of the first step plus work of the second step, and that is equal to a negative 912 joules, or if you like, a negative 9.12 times 10 to the power of 2 joules. That is the irreversible, or the work of the irreversible two-step. Let's use this position up here for the corresponding reversible change and calculate its work. So we'll see this written as work reversible, or we'll see it as work max, because what's neat is when if you went back to the sketch, pressure volume, and in this one, yeah, let's do that again. This time I'm just going to have my initial and my final. P is in atmosphere. Didn't leave enough room. 6.25 all the way down to 1.00. In fact, now here, my starting point really is here, not like on the other one. Have a look back. And I'm not dropping the pressure by a finite amount. In fact, it changes infinitesimally by dP, and I get a corresponding dV. And so you get the tiniest sawtooth coming down here, and the area under that curve is in fact a curve. And so instead of stepping, can I slide this over and just show you for a second? So I'm actually going from here to here in a crazy number of steps, and so I'm not losing, say, that gap. So when you do it in one step, if I were to do this in one step, that would have come all the way down to here first, and then I would have a rectangle that would span, have dimensions of 1 atmosphere by 4.00 liters, in other words 6.00 minus 2.00, and so it would just be the area under here, a much smaller rectangle than doing it as a 2-step. And so I can imagine that as a 3-step, this would maybe come down to here, and then a little bit come down and go to here and do my final step. Do you see? With increasing number of steps, I get an increasing area under the curve, and the limit of that would be, I guess, the limit of the tiniest change that I can make, and therefore the area under the curve now becomes the maximum. And that's why the reversible work is called the maximum work. And the formula is a little bit different because, as you know, it integrated differently when the pressure stayed inside the integral. And so it comes as minus nRT ln of V final over V initial. A quick check, we know that V final is 6.00 liters, V initial is 2.00 liters. The temperature is isothermal. I'm going to go back and add it because it wasn't actually written out, and it would need to be given to you. It's 298 Kelvin. What we don't know, though, is N, number of moles, and it's interesting that the work on this side didn't actually depend on the number of moles. It just depends on the volume and the pressure. So what do I do over here? Well, this is, okay, because I don't know what I'm going to put in for this, but this is a perfect gas, and so I know that PV is equal to nRT, and I can rearrange for N as PV over RT. Okay, now, just want to point something out. Say that I thought, oh, I'll just throw that into the formula. So I'll put PV over RT, and look, the RTs are going to cancel, then I'm left with PV. And then you go to put in your pressure and your volume for, and then you stop and think, wait a minute, that's not right, because pressure and volume were changing. They stayed on the right side of the integral sign. In fact, I integrated them, and my solution was the ln of V final over V initial. And pressure didn't stay there in a way. It was re-expressed as nRT over volume, and so the volume stayed behind. The nRT, which is constant, came out in front of the integral sign on the left. So we don't want to go in circles here. And so what we would do in this case is actually take P1, V1, and T1, T1 is constant, and put it in here and actually solve for the number of moles. Yeah. And so the pressure is, remember now this is, well, I guess I could use any of these because n is constant, but let's just take the first point. So P1, V1, and T1. Pressure 1, 6.25 atm. The initial volume, 2.00 liters. Divide by 0.08206 liter atmosphere per mole Kelvin, and the temperature 298 Kelvin. And so the number of moles is equal to, let's do that. I'm going to reach for my calculator. You can do the same. 6.25 times 2 over 0.08206. You can hear my keyboard. I'm using the computer. And that's divided again by 298.511. The next digit is a 1, so 3 sig figs is 0.511 moles. That's what I'm going to take forward. So now this whole expression comes down, and now I'm ready to do it. 0.511 mole multiplied by, this time my value of R is 8.3145 joule per K mole. I don't want the liter atmosphere per mole K. If I do, then I have to do a conversion with the 101.3, so I'll just use the right one. Temperature 298 Kelvin times, all of that times the ln of the ratio of the volumes. The final was 6.00 liters and the initial is 2.00. So you can put liter and show that they cancel, but you'd have to actually cancel them because you cannot take the ln of units. You can only take the natural log of a number. Okay, back to the calculator you go, and we get a value of, and don't forget that negative sign is carrying forward because that ratio, ln of that ratio, is not going to be negative. And that's good because I am expecting the work to be negative, so that keeps coming down. 1391 joules. And just to go back for a second, moles, go out with moles, Kelvin, Kelvin, and those went out, so I was left with joules. To 3 sig figs, it is 1390. No, excuse me, what am I saying? To 3 sig figs, it'll have to be, that 9 will influence the 3. And that just stays 1390. If I went to 2 sig figs, sorry, I'm having a mental block, then that would have been 1.4, but I can keep it as 3 sig figs, and so that's 1390, or a negative 1.39 times 10 this time. Okay, If you want, you can also, let me do another alias here, 1.39 kilojoules. Make sure when you're writing the prefix letter K for kilojoules, it's a small k, so he has a tall tail on that. And that's my answer. And then you want to make sure that in fact your maximum work, here's how you can check for a little error. Say we got some of the points mismatched here and that 0.5 was not the right value. And say if it came out a little lower than that as an incorrect number, and that would make this lower, you would definitely want to investigate your calculations, review them if you happen to calculate the maximum work and it was actually less than over here. So we see that for this reversible process, I've got 912 joules for 2 steps, and that's indeed less than the greater than 1,000 or 1390 joules over here, and they're both negative. So that's how it's done. That's how it's sketched. And if you wanted to put it all on one set of axes, for example, I'm just going to maybe use this highlighter pen to add, and it would be something like that. Not quite a straight line, just a wee bit of a dip so that it's actually a curve. Of course, now the way that I've drawn it, because this is just a sketch, and I've done that wrong. Whoops, I missed the point. I missed the mark, as they say, right here. And I'm not going to delete this video and start all over. So there, we'll take this as a note of caution. So if you are going to put your 2-step and your reversible on one, now I can really see it. Just thought it was because of my poor sketching. But with the highlighter pen, I'm showing, yeah, I actually kind of like this, the whole maximum work. You see that it is indeed greater. So it's got a little bit of a dip in it, a little bit of a curve. This is not the work of the 1 step, right? That's just the work of step 1 of 2. Okay, so let's add one last thing just for the sake of the illustration. So the red is the reversible process. The 2 blocks represents a 2-step irreversible process. And if I wanted to do a single step expansion, well, that would have dropped right to 1 to begin with and then expanded. And if you'll allow me to sketch that, to put that one on there, that's what it would be. So that bottom rectangle would be this isothermal expansion done as a single step irreversible. And the top coincides with the top of step 2. If done as a 2-step, we drop to here, step, 2 steps, the area, total area underneath there would be the area of the 2-step, and then finally you drop it so little that you end up with your curve, and that's the maximum. Great.